Welcome, everybody. Thank you for joining us today here. My name is Norbert Holtkamp. I have the pleasure to moderate this panel, and I'm not sure whether the chair is here. Jürgen? Somewhere else? Okay. He should actually hear this. 2009, the first falling walls, I gave a talk about ITER here, and it's a real pleasure to be back 15 years later and look at what we have achieved in fusion technology. I'm a science fellow at the Hoover Institution now at Stanford University. It's one of the largest and, of course, the best think tank in the United States. My experience is in managing large science projects and collaborations and construction projects. I spent some time at ITER, but also in other places in the early days. I want to introduce this panel with a premise. The premise is that nuclear fusion could transform energy production, ensuring security, driving economic growth while supporting sustainability for future generations. Recent years, this premise has seen remarkable progress in fusion technology, with both private and public R&D projects reporting significant advances. This panel will bring together leading experts from science and management to discuss the current state of fusion technology and outline future roadmaps. I want to start introducing the people that will join me on this panel, and I'll come back to somebody who can't be here today. I want to thank her personally later on, but I will start with Pietro Barabaschi. Pietro, please join me at the table. Pietro is a long-term colleague and friend. He's the Director General of the ITER organization since 2022, the International Nuclear Fusion Project in the south of France. Born in Italy, he has dedicated 30 years to nuclear fusion research, served as the head of the broader approach, Fusion for Energy in Barcelona, and he led the contribution of a major construction project in Japan called the JT60SA, superconducting tokamak, that's just commissioned a year and a half ago, and has also worked on the joint European Torus in the UK, and played many leading roles in the fusion community in the US, Germany, and Japan. So thank you for joining me. Our next guest is Kim Budil. Kim, please join me. Kim is the director of Lawrence Livermore National Laboratory in the US, a neighbor in many ways, making her the first woman to hold this position since the lab's establishment in 1952. Budil studied physics in the University of Illinois as a PhD from the UC Davis, and she joined Livermore in 1987 and has held many leadership roles, finally overseeing the nuclear weapons program. At the lab director, she leads a workforce of about 8,700 or so people and an annual budget of $3 billion. Focusing on advanced US national security, cutting-edge science, and fusion energy research. And came to fame, really, in 2022. We'll talk about that. Next guest is Constantin Häfner. Constantin. Former colleague, or still colleague of Kim, but former employer of Livermore, and now managing director of the Fraunhofer Institute for Lasertechnology in Aachen since 2019. Prior to this role, he led an advanced photon technologies program at Livermore, where he developed some of the world's most powerful lasers. And I'll talk about that. Constantin is a professor at the Aachen University, was elected fellow of the Optical Society in America, and in June 2024, he was appointed as the Executive Vice President for Research and Transfer at the Fraunhofer Gesellschaft. I hope I got that correct. Thank you very much for joining me today. And with that, I think we can actually start. We have a seat that's empty today, or actually took the chair away. Minister Stark-Watzinger was supposed to be here. Unfortunately, she is not. But I want to personally thank her, and I think we should all thank her for her contributions. She and her ministry has done a lot for fusion in the last couple of years. And I think we all hope that this support continues. And if some of you, or all of you, many of you watch German TV, right, Chris? Yesterday, there was a very staunch support made by a leading candidate and a major representative of a big party in Germany, with shows only growing ambitions, building fusion power plants in Germany and in Europe. The BMBF has been a staunch supporter of fusion technology, and Minister Stark-Watzinger called it a sunshot project. That's a term that's often used, was kind of coined by President Kennedy with the moonshot approach. And she said our ambitions should not be too small. And that's what we're going to talk about, ambitions and where we are. The questions that I'm going to ask to every panel member to kind of get into, or that there are specific ones for each of them we're going to go through, is what should the government do to make this really happen? That's question number one. And then Kim and I met yesterday, and I picked up a question. She came back from a meeting in Rome where she told me this was a really good meeting and every country wants to lead. Okay, now which one will? And what does it take? I think that's the second one that I'm probably gonna get around to. All right, Pietro, let's start with you. You're the Director General of ITER for more than 2 years now. 2 years, right? You have taken on this role as a DG. I think everybody is grateful for that at a particularly different time for those that followed the developments at ITER. Major components arrived and had to get fixed. Schedules and costs grew. And I think this is really a good time for you to give us a few-minute summary on the ITER status, and then maybe expand on why you think, and people at ITER think, and everybody else should think that this is still relevant today and still will be relevant in 10 to 15 years.
Thank you.
Please.
Thank you, Norbert. ITER is not new for me. I used to work in the project in the 90s, and I know why and what was, say, the logic behind its conception and design. One logic was cooperation, and cooperation between different people. So that's part of the DNA, but also then there is, of course, a logic in its design. So I came back 2 years ago, and as you pointed out, we had some issues of quality that I think I'm glad to say that are now in the rear mirror to the large extent. We started again assembly. So we have developed a new baseline, a new plan, a new forecast, and a new roadmap. The previous roadmap foresaw the achievement of first plasma at the end of next year. This was a relatively modest plasma current, though, and plasma current is a measure of the magnetic energy, and we will now move through a different roadmap that will entail essentially the installation of all key components, including the high flux components, the diverter, early on, and move, say, to a phase that will be directly leading to the maximum plasma current. So this is the new roadmap. We are now in the execution of the assembly, and you are all welcome to come back. I don't know, Norbert, when you last saw ITER, I think
year ago.
You will see movement now, a lot of movement, and let's say going to the question of say where your question about the relevance. Yeah, I think ITER remains. Its design basis remains the same. That I would say, would it be designed the same way now? I believe so. It is driven essentially by power density consideration to design a thermonuclear magnetic confinement device that would attain its conditions for durations which are long enough to reach thermal equilibrium in the structures with power densities that would be manageable with state-of-the-art technology. And this is one of the great challenges in fusion. We cannot embed the coolant inside the medium that produces power, just like we can maybe with fission or with coal or whatnot. So we have to keep it on the surface, and one of the big challenges is the heat rejection, and that has been the driver for the ITER sizing, to make it big enough so that the heat deposition would be manageable. And I don't believe that there has been any breakthrough. I know that there has not been any breakthrough and in the last years to that end. So the project remains perfectly valid, in my opinion, from a technical standpoint. And by the way, this is the reason why I was happy to come back. I know that it's a very challenging project, but I know it's necessary, so I believe, at least.
Can you say a little word about the development of the industry ecosystem that accompanied the build-up of ITER?
Yeah, that's a very important point. I think ITER has contributed, at least for what concerns, to the largest extent, to what concerns the magnetic confinement technology. It has contributed a lot to develop the supply chain, and a supply chain that I really hope will be supporting also some of the many private sector initiatives that are now coming up around the world. And so we will try to do our best to facilitate this connection between the supply chain and the integrators that are, popping up. And also, we will also try, to provide all the know-how that has been developed in the many years of ITER's development, to make sure that this know-how is shared with the private sector. So we have a number of programs to that end, and both for the supply chain and also from the integration standpoint.
Good. Coming back to the question for the minister, or for forward-looking, what should the government do to make it happen, from your point of view, and which country will lead, and what does it take?
Well, I was in Rome myself, and yes, you're right. Some wanted to express their wish to lead, and but at the same time I heard also that everybody was willing to cooperate, and everybody understand the level of complexity of this technology, and that yes, competition is important, but cooperation, finding the right balance between cooperation and competition is also important. So I think from my standpoint, looking at what is now the new geometry and the new balance between private and public sector, and trying to see how we can consolidate some of the investment in the public sector in a cooperative environment. I believe that the way governments are doing, I think it's pretty good. I mean, they just have to maybe increase the investment if they want us to move faster. I can take the example that I've seen in China, their policy, and how they are supporting, for example, ITER, and at the same time supporting, some of smaller scale initiatives, both at the public and private level, and how they still maintain a strong connection with ITER. I think this is a pretty good examples of balancing, different threads in this global technology.
Very good. Kim, your colleagues have been the first ones that managed to actually generate net energy from a controlled nuclear fusion event. Controlled. By 192 lasers compressing a little tiny deuterium tritium pill. So the isotopes could fuse and actually release energy. It was a big event. It made a lot of press around the world. Created a storm of enthusiasm and funding worldwide, actually, which is great. But you also have been very tempered in your predictions of the future. Generating 3.5 megajoules out of 2 megajoules, it's just enough to boil a few liters of water, right? That's what we have achieved so far. But effectively, it still needed a lot more to generate these 2 megajoules going in. So I think we're all very curious about what has changed since December 2022. And then really, from your perspective, the big laboratory is a big technology transfer organization, very successful one. how can you help to accelerate the path to commercial fusion, to a prototype plant? When will we see it, maybe? And what are the, let's say, the three big things that are needed to get solved before we can really kind of determine the, we'll be there.
Thanks, Norbert. So yes, we had this incredibly important physics proof of concept, which was a necessary step for moving forward, particularly for inertial fusion approaches to generation of energy, but only a first step. So as you said, we produced 3.15 megajoules of fusion energy in that experiment for 2 megajoules of laser energy. It took about 330 megajoules off the grid to run the laser to generate 2 megajoules. Of course, our facility, the National Ignition Facility, wasn't built to generate energy. It was meant to be a scientific facility to explore the physics of ignition. And so in the time since that first demonstration, we've had a number of subsequent demonstrations of exceeding the ignition threshold, ultimately achieving a gain greater than 2 now, so we're above 5 megajoules, with a goal of getting to higher yields so that we can begin to explore the physics of ignition. So right now we're in a regime where for any given experiment, the target will either ignite or not. So it's very difficult to think about, for example, simplifying the targets enough to begin moving to more rapid pace of experimental science. So we can do somewhere between 12 and 15 of these experiments in a year because of the amount of energy that's required and the wear and tear on the laser that entails, and the time scale required to produce these targets. They are exquisite works of art. They're perhaps the most precise objects man has ever created, and that was one of the lessons in getting to ignition, was that the level of precision required in delivering the laser energy, in producing the targets, and in designing the pulse shape that drives the experiment was much greater than anticipated initially. So if we can get to a higher gain, say gain 5, maybe above 10 megajoules, you can begin to explore small perturbations around the target design we have now. And that really has to be one of the goals if we want to pursue fusion energy research. We need a more robust target, and we need a simpler target that can be produced at mass scale. Another element that would go into a fusion energy scheme is rep-rated experiments. So instead of doing one experiment every few weeks, we need to be able to do this 10 times a second. So we'll need a laser system that operates not at the timescales that we're operating today, but at 10 hertz rep rates. And so there are laser technologies that will scale appropriately to get to those repetition rates with the right energy delivery and pulse characteristics. But we need to do a technology demonstration really at scale to understand how that's going to work and how we would build out a power plant. And then there are a set of issues that are common between magnetic fusion and inertial fusion around materials and balance of plant. For us, management of a tritium fuel cycle, as an example, is something we've not really grappled with yet, how that will work to make a closed loop fuel cycle for our system. So lots of work still to do, but really in an exciting place where we can begin to move forward. Now, until we achieved ignition in the US, the budget for inertial fusion energy research was 0. And the idea was that until we had this physics proof of concept, there was no reason to really invest in an energy pathway. So the US has moved out smartly in the wake of our demonstration of ignition. The government announced a bold decadal vision for fusion energy. Again, most of the investment is still going to magnetic fusion approaches, but the budget for IFE, I'm happy to announce, is no longer identically 0. It's moving up slowly, but it is moving up. And as we build partnerships, as we work with colleagues across the US, but around the world, I believe we'll be able to drive that very significantly. It's nowhere near matching the private sector investment today. And that's one of the challenges we face as a community. The public sector research that we're doing to understand these material science challenges, to understand tritium fuel cycle, to really advance the state of the art for ignition has to be done in these institutions that have these large-scale facilities that can really manage that research. So we need much more investment on the public side so we can be a platform to help launch a really successful, for us, inertial fusion energy industry.
Very good. Maybe a few words from you too on, how does this help to develop the, private sector platform? I mean, the industry that supports, building such an infrastructure.
So we can work with industry in a number of ways. One is, again, working with them on technology development, either collaborating with them on their driver technology of choice. And there are both pulse power and laser companies that have spun up in the wake of the ignition demonstration. Another is to work with them to design targets that can work with their driver technology. We have very sophisticated modeling and simulation tools and large computers that most startup companies don't have access to. And we also have, armies of researchers doing things like building AI into our science models so that we can advance the state of the art rapidly. And we have the only facility on the planet currently that can produce these ignition conditions in the laboratory. So if people really want to study that physics and study different target geometries, we need to be able to collaborate with them. So my hope is that we can create sort of a pre-competitive ecosystem where we can work with many companies to really rapidly advance the state of the art, and then they can differentiate based on the technology pathways they want to pursue.
Okay, very good. I asked kind of, what are the three big things? I think if I caught it correctly, you said four: targets, repetition rate, deuterium, tritium fuel cycle, and material science. Okay, 3, 4, whatever.
I'm from a national lab.
That's right. So it's probably a longer
it needs
list.
to be a little more complicated.
More time, longer list. So, so since 2022, can you give us a little bit of feeling of what has been progress in these four areas? So targets, rep rate, DT, material science, where you say, okay, I can see the trajectory.
Certainly in targets, we've made progress, and we're studying several different elements of the target design we're using currently to really try to optimize those targets. Again, with a goal to getting to a higher yield, which would allow us to try to simplify the targets in meaningful ways. It currently takes a very long time to produce one of these diamond capsules that's of sufficient quality to have one of these experiments be successful. In the material science realm, we have made a lot of progress on the production of the capsules. They are much better quality than when we started, and our production supply chain, if you will, is much more robust on that front. Some of the other questions around materials for high radiation environments, things like that, there is work ongoing, and I would say that has been a long time pursuit of the community, and we'll see steady progress on that for some time. Tritium is one area where we've not really done a lot of work yet on how breeding and fuel cycle will actually work in an operating plant. We have schemes and designs, and we need a little more time to really build up the experimental infrastructure to work on those problems.
Cool. So maybe you want to say which meeting you told me yesterday about, since you guys were probably all there, but here's the two questions, right? Back from that we want to ask the ministry. What should the government do to make it happen, in addition? And what, you said it, every country wants to lead. Which one will?
I think the governments really need to invest in the public sector research that will support delivery, ultimately, of commercial fusion power to the grid. And that really needs to be done aggressively and at scale. And so my standard comment on how long it will take us to achieve net energy on the grid, time is money. So to the extent that we have investment at scale now, there are plenty of really smart, capable researchers who want to be part of this journey. We need resources to support them and to accelerate that research. I think there's a role for leadership for many countries because we need technology diversity. This is very hard. So there is no one answer to this problem. And several countries have already staked a claim, putting national programs together. Germany has certainly done that. The UK has done that. The US is doing that. But we'll need international collaboration. I don't see any path that doesn't involve really bringing this community together in meaningful ways to advance the science rapidly.
Good. Thanks for making this very important point. I think that feeds into many panel discussions this afternoon and this morning. So, all right. Constantin, you have a long career in laser-driven inertial fusion confinement. And as I said, for a long time, you used to live in the neighborhood. Recently, on request of the minister, you led a study, an expert commission, I think is the correct word, on laser inertial fusion energy. Published a 152-page report, memorandum, in May of 2023 on what to do. Tell us how it's going. public sector, private sector, there was a clear pathway, right? And in between. And the in between is really the Fraunhofer sweet spot, right? So you're right there in the middle. Tell us about the center of the storm.
Well, the center of the storm is always very quiet, right? So, yeah, I think Germany is in a very interesting position here. We have a long history in supporting magnetic fusion energy, and we're among the world leaders in magnetic fusion technology. And we have, on the inertial fusion energy, we haven't had a program. So our program was 02. But we also didn't have a defense program on the other side that was supporting some of the technologies. But interesting enough, the German industry is really leading in a lot of the laser and optical technologies. And that's because there was a very strategic investment in the 80s into promoting the laser for industrial applications. And so there was a lot of research, done and fostered by the government to enable the industry to make that transition into precision manufacturing with lasers. And so that led to a very powerful industry. So, Germany is a world exporter of lasers. Has about over 40% of the market shares in Europe with respect to the photonics market. And so it was clear that when the breakthrough, the first breakthrough, happened actually on 808 in 2021, which was meeting the generalized Lawson criteria. And already then, Fraunhofer started to think about what are the technologies in Germany, in industry, because that's our job to enable industry, that apply to this fusion approach. We're already invested in the magnetic fusion energy and enabling the technology there. But now, the laser stuff was the new kid on the block. And sure enough, we did not know whether this experiment could be repeated and enhanced in yield, but it was worth a shot. And so we developed the first market view on what this would look like, because what we see behind inertial fusion energy and magnetic fusion energy is a huge supply chain that needs to be built. And that's a high-tech technology, and high technology is actually in the genes of Germany, and so this is one of the things we have to get into. So then the other thing what happened was that the private industry was pushing very strongly ahead on building up startups and different approaches to fusion energy, where a lot of promises were made. 5 years to the grid, 10 years to the grid, to a power plant. And so the ministry asked us to put together basically a position analysis of where Germany is and where it needs to go. And that's what led to the memorandum. And we kicked it off exactly on the day, that was by accident, when NIF actually ignited. So that was a good sign. And
I thought it was a plan.
Did you plan this? Well done. And the impressive thing since then has been, so the 150 pages turned into about 10 million a page, today in funding in Germany. So I think that is, very remarkable, and you can see how quickly actually the government was really going into this, and with support from the industry, in really going after this as a mission, right? So I think that is a massive change, a massive acceleration, and that's what the field needs. And it's a statement, right, which we were asking from the government, make a statement that this becomes a mission. And so they did, and so I think that's a really good change. The second thing what happened is NIF keeps igniting and getting up the yield, and so this is a very robust platform. And then the third thing is we're growing the industry, and so we can see now, there's an investment of about 9 billion as of like a week ago or so, in private industry venture capital invested into these startups. And so I think the whole world is actually starting to accelerate, and the World Fusion Energy Group, which was founded 2 days ago, we're all in Rome there for that, was also a strong signal to the world. 36 countries made statement that they want to support fusion. And so I think, a lot of things have happened, and we're just at the start of really moving into an accelerated pace towards a fusion on the grid. However, let's not forget, there's a lot of research that still needs to be done, and it's a real marathon. And so getting behind this now, we're all excited, but there will be the time where the hype stops. And that's when we need the sustainment, and that's one of the job of the government.
We'll talk about that too, I think. So talk a little bit more about the special role or the new role that you have and about Fraunhofer. Fraunhofer is a very unique, way of doing business, right? 50% private, more or less 50% government funding. And now Fraunhofer is in the middle of this technology development, bridging industries. What is this new role that you bring with it? What do you plan to do, and what special role does Fraunhofer play in this technology transfer and building up the technologies?
So, the Fraunhofer model is a very unique model that is, a lot of countries are actually very jealous about the Fraunhofer model. The idea is actually, to have about a third in funding, and a third comes from industry and it's contract research. And this is really our job, to bring technologies, mature technologies, so that they can be scaled in industry. And that's about 1/3 what we do. Some do 40, some do 30, right? So this is roughly, the operating point. Then another third comes from government, and that's where we lean forward, right? We need to think about, like, what is the next thing that has to go into the market, right? And so we actually scout technologies that are being developed at the universities. We work very closely with the university systems or with the other organizations like Helmholtz and Max Planck in order to identify technologies that can go into the market, right? And then the next third is competitive funding, where we basically jointly work with universities or alone or with other organizations or internationally to advance certain exploratory research that will enable industry in the long term. So we always have this mission of having applied science application in the market. And by that we're kind of similar to like what the national lab does, right? We don't have the security mission, or we have a little bit of the security mission, but we don't have a security mission like like Kim's lab has, right? But we have a mission really to advance technology and bring it into the market for the benefit of industry, mankind, society.
Great. So one of your colleagues said, I think he's also a head of a startup, that once the laser and target development succeeds, the rest is engineering. I'm not sure I get the words exactly right, but pretty much right. Don't want to say who said it, but would you agree?
Well, it depends, what time frame we're talking about, right? If it would be really that slow, that we would only develop the laser and the target science while everything else is already done somewhere else, then this would be a true statement. But of course, Kim gave us a really good list already for inertial fusion energy, what needs to be done. And that said, actually, inertial fusion energy is just one of the approaches. The magnetic fusion, the tokamaks or the stellarators, two different approaches, or is a different approach. And then there's a whole, two handful of other approaches. The magnetic fusion, the tokamaks and the inertial fusion, the laser fusion, they're about on par right now with respect to where they are in the technology development towards, a sustained fusion power plant. And I want to say this and stress this out because there's areas where one is further and there's other areas where the other one is further. And so at the end of the day, if you compare the technical readiness level, they're about the same. And so this is why we can't down select right now which approach is the right one. And we've got to keep promoting both of them until we get to the point where we identify the first winner. And I think there will be many winners actually in the long term.
Okay, very good. I hope there are. So question to you too, what should the government do to make this happen, and who will lead?
Well, so I think what the government needs, so the first things we've seen in Germany, the government has done actually really well, which is like they got behind fusion, they made it a public announcement, they provided quickly a funding, and they are in the process of building the fusion ecosystem because they make it a mission, and so that's important. The things what still need to happen is we need to find the right vehicles for international collaboration. And that's a very tough one because we're touching on many fields like dual use and proliferation, export control, competitiveness, and IP. And that's very difficult to manage, and we have quite a bit of experience with that, working in both worlds. The next thing what we need to do is we also have to enhance fundamental science, because we just have to build a larger workforce. They need to be trained. So we need to also build infrastructure that we share among private and the public sector. And so also become sort of like the source of truth, which is important because right now we're seeing a lot of people making a lot of promises, and I understand that, right? But at the end of the day, we all have to be aware of like it is hard and it will take time.
Okay, very good. So we had two laser people, one end of the fusion spectrum, right? One way to commercial fusion. I want to come back to magnets a little bit. It was already mentioned, right? The two big sectors, inertial fusion driven devices and magnetic confinement. You talked about this a little bit, Pietro. ITER uses large superconducting magnets to confine these plasmas, right? It's actually very impressive. Each magnet, I think I still remember this, 18 of those big things is a big Airbus, right? Something like that. All being delivered to the site right now. What do you think are the biggest impediments to magnetic fusion going forward? And how does this phenomenal development on high field magnets, high field superconductors, high field low temperature superconductors play into this game? And I think that you are very well suited to answer that question because Pietro is one of these fusion supercomputers. You can ask him a question and he actually knows what he talks about because he calculates it in his head. So I don't know how he does it, but can you tell us a little bit how this plays together?
Okay, so the magnetic field is there in magnetic confinement in order to provide the conditions to then develop a plasma pressure. And the plasma pressure that develops and should be sustained in an equilibrium, to some extent, it will be actively controlled because to get performance, just like in a fighter jet, you have to push the limits of stability, and you need very fast control system. But the magnetic field is there in a tokamak, essentially in magnetic confinement to provide stability to this, to the plasma. There is an important factor which is called the beta, which is the ratio between the thermal energy of the plasma and the magnetic energy. That is something which measures, to some extent, the efficiency of this control. And tokamaks, have a relatively low beta and say a few percent, so they require massive magnets. And you're right, the one of ITER is actually the biggest magnet in the world by far. It has 4 times the energy of the LHC in CERN. It is about 40 gigajoule, which is equivalent to the kinetic energy of 4 jumbo jet at cruising speed. So it's really massive amount of energy which is stored in order then to be able to produce the 500 megawatts or contain, and stabilize a plasma that will then produce 500 megawatts. So it looks like, okay, we need magnets which provide more performance. And that has been the driving force behind the development of niobium-13, which is, I was asked what was a breakthrough. I think this was a real breakthrough in the history, the development and industrialization of niobium-13, because it's what has allowed to have such powerful magnets. Now we are in a new phase, which is the use of different, alloys that allows to reach high field, such as niobium-13, but at a higher temperature. I think this will drive in the direction of having more cost-effective, creation of this magnetic field. But I am not convinced that this will be a real breakthrough in terms of, enabling a next step in the physics and in the value of beta itself. And what is the... So I wish that magnet technology would essentially be the breakthrough that would allow the development of fusion, because I believe there is a lot of room for improvement in magnets. Magnets, the idea of having high magnetic field is not new. I mean, in the 80s and 90s, there were alternatives to ITER, and some were pushing for that, or different lines which were thinking about having high density. We speak about the triple product, anti-tau. Temperature is normally what it is in fusion. So we have to play with density and energy confinement time, and the possibility to operate at higher density was already foreseen, and there is actually no technological barrier at the magnetic field that we operate in ITER. We can go at higher field, no problem with that. Maybe not in ITER, but using the same type of wire. The problem associated with that is what I mentioned briefly before, is power density. You spoke about the sunshot. Yeah, I mean, you don't want to get too close to the sun, as you know, somebody learned in Greek mythology, because you're going to get burnt. And there are important boundaries associated with power density. So I remember a professor I had in university, when I was already sort of interested in nuclear fusion. He said, you know, the power density is the problem. And he was very pessimistic, by the way. He kept telling me that fusion is a technology which has a lot of promises and zero chance of success. And I'm trying to prove him wrong, by the way. That has been the leitmotif of my life. But I think it's not the only one. You know, he was not the only one, I think, thinking like this. But now we have a lot of hope. But power density remains a real issue when it comes to reliability.
So if I get this correctly, right, power density mean when you compress when you make the same amount of energy in a smaller volume of plasma?
Pretty much. That's, I mean, the scaling factors.
So this question of compactness and
so I am more of the view that eventually maybe this will allow us to lead us to say getting steady thermonuclear conditions. But when we want to not only get more energy out than we put in, but when we want to get more money out than the one we put in, then we have to live with issues of reliability, because we don't want these facilities to run for a couple of days and then shut down for 6 months. So in this respect, I am more of, rather than of the image of the Formula One, I am more of the image of sort of, truck engine, with a lower power density and bigger size, and maybe a technology that doesn't allow, a too refined type of manufacturing.
Okay, great. So to kind of close up, get to the question to the audience here. I think you mentioned it, Constantin. Private investment have skyrocketed. I think 2013 there were like 10 companies maybe in the fusion business, and I don't know, a few 10 million maybe. Today we have more like 40 and close to 40 companies and close to 9 billion in private sector investment. It's distributed still over a small company. I mean, the big numbers are with a few companies, right? So it's not equally distributed, obviously. But the question remains, and I think as part of the Q&A also, and the previous panels, Europe suffers from regulations. I think that came up several times this morning. Regulations is something people have worked on. Regulations, is that something, and international collaboration, that's in control in Europe? Yes or no answer?
I'm not sure I can answer yes or no here.
Okay, maybe.
Maybe.
Okay, yes or no in the US?
More or less, yes.
Okay, Constantin?
Well, Europe is very diverse, so not yet.
Not yes, okay. Very good. All right, with that, I think we'll open it up to the panel and see whether there's any questions from the panel, which there should be, and I'm sure they are. Anybody? Yes, please. Just wait for the microphone, please. Introduce yourself.
Guten Tag, or hi, my name is David. My question is, to what extent AI, given that it's such a buzzword, and I think also in the context of nuclear fusion, especially finding the conditions, especially I think in magnetic nuclear fusion, there were some advances. Just in terms to what extent is there a promise that it might help us to actually achieve this goal in a faster way?
Okay, very good. Who wants to pick it up?
I can start. I think it's a very good question. And I really have a lot of trust on the, the next, let's say, few years in the deployment of AI in our technology. It is a complex system, and any complex system, from my experience, is the one that benefits the most. Complex because there are so many interfacing technologies, and so the optimization itself is so complicated that I believe that AI in the modeling and in as much as the optimization of the engineering will provide us with very good ideas. And we are in the at least in ITER, we are in the phase of deploying some of these technologies, also to help the private sector to gather the information. Just as much as I can take the opportunity to inject another concept is additive manufacturing. I think this is another technology which will really support the reduction of costs.
Good. Next question. Anybody else? Yes.
Thank you. Bob Rosner, University of Chicago. There are two topics that didn't get much attention. One of them has to do with the challenge of energy extraction, for which none of the experiments are really designed to address. And I'm just curious about what you think about the path toward that.
Okay.
And the second question has to do with timescales. So I have to say I was very impressed that none of the speakers, including the moderator, said a word about the timescales.
Well, the moderator is not supposed to say anything. So,
yeah, maybe that was the question.
Rob, let's quickly go around because then we need to really close up. So, energy extraction and schedules. I think actually Kim did talk about schedules.
So I
more money, shorter schedules. So
time is money. That was my time scale.
Right.
On the energy extraction question, it's different for magnetic fusion than for inertial fusion. It's one of the potential benefits of the inertial fusion approach is that the target is separable from the driver. So you can have all your high-value driver equipment physically separate from the chamber where you're generating the fusion reactions, making it somewhat more simple to think about operating a plant, maintaining a plant, and doing energy extraction in that environment. So.
Okay. Anybody else wants to kick in here?
I think it's just a very quick answer. It's just how much you need it. It's a level of commitment, and that's I think we're doing well over the last 2 years, specifically in Germany. But the rest of the world has to crank it up because the problem is so hard. And Kim mentioned that it needs diversity in thinking, and it needs diversity in workforce, and it needs a large workforce. Right?
Good. So I think the schedule question we can defer.
I think it's a
that's
good question.
Privilege of the chair of the panel, but we can have a conversation about it.
We can speak
later. We can speak privately. So let's come to the last thing, which is really our question: what is the next step to break down the wall to? 10-second answer.
Yeah, I think AI will break down some walls. I'm pretty sure about that. I don't know which ones, but I think they will open up some new fields.
Excellent. Kim?
A new kind of public-private partnership, a way to really act as an accelerant and a platform to launch these companies smartly forward.
Very good. Constantin?
Engineering gain. And I think, so that means like a power plant can sustain itself. And I think for that, we need to make fusion a mission for mankind.
Very good. My answer is, it takes all of you, not only the experts, to support it and get this idea of international collaboration, science, and technology going. Thank you very much for coming to the Falling Walls. Thanks to the panel members.